Hi folks, welcome to physics class. I hope you all are doing well. It's a little bit weird to do this on a camera instead of face to face. I wish we were all setting up actual circuits and analyzing them together with light bulbs in class, but I guess this will have to do for now. So I wanted to start lesson 2 by a brief review of the lab that you guys did during lesson 1. I had you all set up some online circuits, you did some analysis, and I want to talk through some of the observations that you guys made. Some of you guys made some fantastic observations, and I wanted to talk through some of the important nuances that you found with setting up some simple circuits before we get into a little bit more complicated analysis. We're not going to get super complicated, but let's go over some of the basics that you guys saw in the last lesson and then talk about how they're going to apply as we start putting some more numbers and equations onto what we're looking at. All right, the first circuit I had you all build was this one, and you noticed that when you open the switch, all of those little electrons flowing through the circuit are really just sitting there. We don't have any bulbs on, but when you close the switch, now all of a sudden you get a current flowing, you get the light bulbs lighting up, and you guys were able to then analyze some of the voltage and the current as we're going around the circuit. So I had you pull out the voltmeter first and measure some current. I named a number of points going around the circuit. We called these 2 points sort of A and B up here around the corner. And what you should have noticed as you were doing this lab is that there is no change in voltage as we go around this corner of the circuit. If you remember what voltage means, voltage is the energy per charge. So you can think of that as like the energy per electron. And that's not changing as we go around this corner. And if you think about why not, the reason why not is that nothing in this part of our circuit is using up energy. Nothing in this part of our circuit is giving the electrons energy. And so their energy is not changing as they're flowing around the circuit in this region. The voltage, there's 2 probes. We're always measuring how much the voltage or how much the energy has changed between these 2 points. So nothing has changed. We haven't gained energy, we haven't lost energy. The next 2 points, points B and C, I believe we called them, were down here. And when you move the probe from here to here, what you end up finding is that now our change in voltage is negative 4.5. That means that we have lost 4.5 joules per coulombs, 4.5 joules for every charge. So our charges have lost energy as they've traveled through that light bulb, which makes sense because the light bulb is using up energy. Okay, I then had you move the probes over here like this from points C to point what we call D, and you found that again, the voltage should have changed by negative 4.5. We've lost another 4.5 joules per coulomb or volts as we're traveling through the circuit this way. This light bulb used up the same amount of energy per charge as the other light bulb used up. So we have negative because it's used up the energy. And it's the same kind of light bulb, so we've used up the same amount of energy per charge. Okay. One of the observations that a lot of people made was that if you put these probes the other way, so if we put the black one over here and the red one over here, for example, we get the same number. We get 4.5, but it's positive now instead of negative. And that's important. The negatives and the positives mean a lot when we talk about voltage because we're always talking about has the voltage increased or decreased between these 2 points on our circuit. Typically, when we talk about current going through a light bulb or going through a motor or a resistor, anything that's going to be using up the energy, as we talk about the current flowing through that thing, we are going to talk about that current losing voltage. It's a negative voltage. The voltage is going down because that thing has used up some of the energy. I know the direction of the current is a little bit confusing. I'm not going to be picky about which way you think about the direction of the current, but the typical direction of the current, if we put this as a conventional current instead of the electrons moving, is the conventional current is going this way. And so that's typically how physicists talk about the direction of the current. If you've taken an engineering class, they'll talk about the current going in the opposite direction because that's the direction the electrons are actually flowing. Physicists like to think about them as positive charges moving around, even though their positive part isn't moving. It gets a little bit confusing. I don't care which way you talk about it. or visualize it. But when we're talking about the change in voltage as our current goes through a light bulb, I would like you to think about that as a negative change in voltage because the voltage is going down. Okay. The opposite is true when we look at the change in voltage over a battery. So if you looked at the change in voltage across this battery, now we have a 9 volt, and think about this as a positive voltage because as the charges go through that battery, they are gaining energy. That's the purpose of the battery in the circuit, right? Is that they are giving each of the electrons or each of those charges some energy so that as they then travel through the light bulbs, they can light them up. Or if they're going through a fan, they can make the fan spin or whatever the case is. So if you had had your probes going the other way, you would have talked about this as a -9. Maybe you wrote down -9 for the voltage here. And a lot of you guys noticed that on that last question, when I switched where I had you put the probes, you got a negative versus a positive value. Again, same number, but just a negative positive. In general, think about the battery giving energy or giving voltage to the current or to the charges as they flow through the circuit. Okay. Some of the things that you also may have noticed was that this voltage that our battery has given our circuit is 9 volts. And if we look at how much voltage each of these light bulbs used up, if you remember those numbers, they were both 4.5. So if you think about how those relate to each other, we gained 9 volts, then we lost 4.5, and then we lost 4.5 again. And 4.5 plus 4.5 is 9. So we've lost all of the voltage that our battery gave the current. And then we start back over. Our battery gives it another 9 volts, and then it uses it up as it goes around the circuit. We'll give a name to that later. We'll talk about that as one of Kirchhoff's laws. But this idea that these things add up and we use up all the voltage as we go around one loop of the circuit is going to be important as we analyze circuits later. Okay. I also had you all pull out the amp meter and put this crosshairs on the wire. And what you should have noticed as you traveled, moved this crosshairs all the way around your circuit was that the current stays constant. It's 4.5 amps. Whoops, left the wire there. It's 4.5 amps no matter where you are. You're on the switch, you're on the wire, you're in the filament of the bulb, you're on the wire, you're in the middle of the battery. The current is the same absolutely everywhere. And that is often a little bit counterintuitive until you think of what current means. Current is not measuring the energy. It is not measuring how much energy any of these charges has as they're moving around. It's just measuring how many charges are flowing past per second. Remember, it's coulombs per second. It is the number, you can think of it as the number of electrons or the number of charges that are flowing past a particular point. And in this circuit, the way this is set up, there is no other paths for the electrons or the charges to take as they flow through the circuit. So if they're flowing through this point, they're going to go right around the corner, and they're also going to flow through that point. So you can't have more electrons flowing here than you have over here because it's all one path. Same thing over here. The same number of electrons are flowing here before the bulb as we have flowing after the bulb. They've lost a little bit of their potential energy as they gave off some light, but there's the same number of them flowing at the same speed because the bulb is not using up kinetic energy, it's using up potential energy. So there's the same number, they're moving at the same speed, and so the current is exactly the same anywhere you go. The last thing I asked you to do in this lab was to look at the relationship between voltage, current, and resistance. And you did that one at a time. So I first had you click on the battery and change the voltage of the battery as it looks like in this screen. You could change that voltage going up or down and look at, when you did that, how does the current change? I didn't ask you to write down a table of values, but if you had, you would have written something like this. And I think everybody noticed that as you make the voltage increase, the current also increases. A lot of you noticed that it was exactly proportional, that the voltage was always 10 times more than the current. And we can write that as a mathematical relationship in the orange down there. Current is proportional to the change in voltage. And remember that orange fish-looking sign means proportional to. It just means that the current is always equal to something times the voltage. We did the same thing by varying the resistance and looking at how that changed the current. So you clicked on the light bulb, you could scroll and change the resistance up or down, and you looked at how that affected the current. And you found that that was an inverse relationship. Again, I didn't have you write down data, but if I had asked you to, you would have written down something like this, that as the resistance goes up, the current goes down. The higher the resistance, the less current. And that makes sense based on how we kind of defined resistance as opposing the flow of current. If there's more resistance, there's going to be less current. This relationship is an inverse relationship. So current is inversely proportional to resistance, or it's proportional to 1 divided by resistance. These two relationships are put together in what we call Ohm's Law. Ohm's Law basically combines these two ideas and pulls them into one equation that allows us to do some calculations. So it says, well, if current is proportional to voltage and it's proportional to 1 over resistance, then current is voltage divided by resistance, and it writes it as this fraction. So I equals delta V, the change in voltage, over R. A lot of times we'd rather have it as an equation without a fraction. So we can solve this for delta V, multiply both of our sides of our equation by R, and we get that the change in voltage is equal to the current multiplied by the resistance. Ohm's law is one of the most useful equations that we have when we look at circuits. It tells us how to calculate the changes and the expected currents and voltage we'll have, and we're going to be using this equation a lot.